Today we are going to do section 2.3, the dot product. The dot product is, what is it? It's just, look down at the definition, is when you have two vectors, you're going to multiply each the corresponding components. That is, if you have u equals to u1, u2, u3, and v is similar, well, the dot product is simply you multiply u1 times v1, u2 times v2, u3 times v3, and then you add it all up. And why are we doing that? That, by the way, gives you a number. That the result is not a vector. Okay, it's just some number that you added up. And there's a purpose to doing this because there are certain benefits. But before we consider the benefits, let's please do example 2.21 as part of your homework. Now the next page, let's look at theorem 2.3, the properties of the dot product. Being that the dot product is stuff that's multiplied and then added, all the regular properties of multiplication and addition carries over. For example, u dot v is the same as v dot u, because it doesn't matter how you multiply and add those the components. And then if you have u dot v plus w, it's the same as u dot v plus u dot w. If you have a scalar multiplied by u dot v, that's the same as the scalar multiplying by the first vector first, then do the dot, or multiply, then or do the dot multiply by the second vector first, then do the dot. And then and lastly, a vector dotting itself is the same as the square of the magnitude. That's just how, you imagine that. What is that? That's just u1, if you have a vector multiplied by itself, that's u1 squared plus u2 squared plus u3 squared, right? Because it's multiplying by itself, added up. That just happens to be the square of the magnitude, which by the Pythagoras theorem is the square root of those things squared, and then you take the square root. So the dot product is the square root of the magnitude. So that all works out very nicely. Please look at the proof a little bit. I'm not going to go over it because, as I mentioned, those are, because the dot product's definition is so simple, that all those properties, basically you can see it coming. So please look at it a little bit, and then do example 2.22 as part of your homework. And then going to the next page, we are going to look at theorem 2.4 on page 149. Now we're on page 149, theorem 2.4, which states that u dot v is the same as the magnitude of u times magnitude of v times cosine of theta, theta being the angle between u and v. Now that is, the question is, that gives the one use for the u dot v. What do we need it for? Well, we can, if this theorem shows that you can calculate the angle between two vectors by using u dot v divided by u times v. So we need to prove this. Now first to prove this, here's my two vectors, okay? U here, v here with a theta in between. And I need to figure out what v minus u is. What is v minus u? And because that's going to help me with doing this stuff. Now v minus u is, by definition, is the vector from here to here. By the triangle rule of the previous section, here's v minus u. Okay, why? Because the triangle rule says that this thing plus that thing equals to this, right? And it does. If you have this part being v minus u, then the u cancels out and you get v left. So that v minus u is this part. So what we're proving is that what we're going to prove, first we're going to quote the law of cosines. What is the law of cosines? The law of cosines states that if you have a triangle ABC, where this is C, okay, this is angle theta, and this is A, and this is B. Now, the capital letters I have here represent the length of the sides of the triangle. So the law of cosines states that C squared equals to A squared plus B squared minus 2ab cosine c. That is the good old law of cosine. If you don't remember it, just believe me, this is what it is. Okay, sounds familiar because it's right. Now, so then we're going to calculate, we're going to use the law of cosine to prove this thing. So first, we're going to calculate the magnitude of v minus u squared, okay? Because v minus u is our third side. So, and we don't need to know the magnitude itself. We just need to know it's squared because we're applying the law of cosine, where everything is nicely squared. So v minus u, we'll calculate v minus u squared. And the absolute value means the length or magnitude of the vector. That is going to be equal to, first, we will go for some property we just had. One of the property that we just had says that vector the dot itself is the same as the magnitude squared. So we'll use that property and say that we'll do v minus u, and we'll calculate its value of it dotting itself, v minus u. Okay, and then we'll apply more properties that we just gone over that I claim was obvious. That is all the general properties that we're used to all apply, which means that that is the same as, we'll break this up, that equals to, well, we'll follow what the book does. So this equal to v minus u. First, we'll dot the first one, okay, dot v, and then minus the same thing, v minus u dot u. We'll dot each one, okay, and keep the minus sign on the outside. And then continuing, we will have, keep doing this, we have, so then we have v dot v, and then minus u dot v, minus, what is that, v dot u, plus, and then u dot u. So far we're still using all those properties that we just that I just glossed over. But it's I'm saying that this follows what we are used to. Okay, the properties are all the same, so we don't have to think too hard to come up with that. And then eventually we remember that a vector the dot itself is the same as magnitude squared. So we're going to do that. So this is squared, and it's the same over here, right? U dot u is the same as the magnitude u squared. And then what's that stuff in the middle? Well, the stuff in the middle, being that u dot v is the same as v dot u, so then we have two of these things. So this whole thing comes out to be similar to what we're used to, a normal algebra, whereas this is doing vectors. But it works out the same, and then so it equals to 2u dot v. So, and in doing this, we have used quite a number of the properties that we just learned, but nevertheless sort of repeats what we had. Now that we have this, we're going to plug it into something. That is, we're going to apply the law of cosine, which states that now we're considering just the length. Okay, we're no longer considering the vectors, but we're considering just the length, the fact that these three vectors form a triangle. So the length of it, then we plug it into the law of cosine, states that the length, then that's, okay, we'll take c equals to v minus u, c squared is v minus u squared. So c, this is c, v minus u, the magnitude squared equals to, plug everything in, so then we have magnitude u squared plus v squared. Okay, we're talking about the law of cosine. And then minus 2u v cosine theta. All right, so far so good. And at this point, then we are going to plug in what we just came up with, this stuff right here. So we have, now look at this stuff. Okay, this is v minus u squared because we just did it down here. And if you were to plug it in there, see, there's v squared and u squared on this side, v squared u squared on that side. So we're going to get rid of that, and kept only this. So we have, so on this side, the only thing we have left is minus 2u dot v. And on that side, we have This disappears. We have minus 2 u v cosine theta. Now keep it very clear what we're doing here. Okay, the dot means the dot product for vectors, whereas without the dot, that's just regular multiplication. Okay, these are not vectors, these are vectors, but for dot product, when you do the dot product, vectors turn into some number. And so that's why this equation makes sense. Now, having done, now by the time I done this, see, I am done. I have proven this is the same as the equation, right? Once you get rid of the minus 2, then we're good. And that gives the equation of the cosine. That is, if you want to figure out what is the cosine of theta, when theta is between the two vectors, then you copy this thing down. That equals u dot v divided by the magnitude of u times v. Magnitude of u times magnitude of v. Okay, so that is the the way to calculate the angle between the two vectors, in case you need to do that, which you will need to do that in your homework. All right, and in fact, you're gonna need to do it right now. To do example 2.23, please do that as part of your homework. Now the proof is somewhat cool, but to apply it takes nothing. Okay, you just to calculate the angle of two vectors. Well, you do the dot product, then calculate the magnitude and do the division, which is what the example does. So please do that as part of your homework. That's 2.3, and then we move on to, what's this? All right, next. Next, let's look at page 151, where we have the bunch of different angles. Of course, theta, if this is the cosine theta, there are different situations. For example, theta might be less than 90 degrees, right? In which case, the cosine theta will be bigger than 0. If theta is bigger than 90 degrees, the cosine theta is gonna be less than 0. And then eventually, if these two things are lined up perfectly so that they don't, so that the angle is 0, then the cosine theta is going to be 1. But if the vectors are completely perpendicular, then cosine theta is going to be 0. In fact, well, yeah, because that's how you prove that two vectors are perpendicular, is when you take the dot product and calculate the cosine theta, and if cosine theta equal to 0, then they are perpendicular. And that is actually theorem 2.5, where it says that non-zero vectors u and v are orthogonal vectors if and only if u dot v equal to 0. Now, the if and only if is a way of saying two sentences in the same sentence. You're combining two sentences in one to save time or be lazy. So the way you understand it, it means if vectors are orthogonal, meaning perpendicular, then u dot v equal to 0. Flip side, if u dot v equal to 0, then the vectors are orthogonal, meaning perpendicular. Now so please do the proof, which is fairly obvious or straightforward, and please do that as part of your homework. And the book does mention, and want you to know that orthogonal, perpendicular, and normal are all words that means perpendicular. Then that is things that intersect at right angles. So why do we have 3 words? Well, tradition, okay? And mostly vectors are called orthogonal if they're perpendicular. Lines are called perpendicular if they're at the right angles. And normal is expressed with, is used for a plane. Like if one plane is perpendicular to the other plane, like my hand with my tablet, then it's called normal. But even then, that's not guaranteed, I don't think. It's just mathematicians just like to use 3 words to mean the same thing. Okay, so we will. So that's something you do need to remember, is that orthogonal, perpendicular, and normal all means perpendicular. All right. So with that, please do example 2.24 as part of your homework using, of course, this theorem. You're supposed to figure out if something is perpendicular. Well, do the dot product, figure out what the theta is. If theta is 90 degrees, then it is. And then, of course, that doesn't do more than just perpendicular. In general, the next example, 2.25, if you need to measure the angle between two vectors, perpendicular or not, well, you use theorem 2.4, u dot v equals to uv cosine theta in magnitude, then you got it good, okay? A quick, easy trigonometry question. Now let's move on to page 153 at the bottom, where we are giving a definition. That is the angle formed by some vector and the coordinate axes, that is the x-axis, y-axis, and the z-axis. It forms three angles normally, right? Those angles are called direction angles, and then the cosine value of those angles are called direction cosines. Now if you imagine doing something like that, you can quickly see that those three angles will determine which way your vector is going. There's a picture on it on the second page, okay? But that is a 2D picture in a 3D object. Basically, once you figure out what the angle is against all three axes, that fixes which way this thing is going to be. That is, you figure out what angle is with the x-axis, okay? So you turn this way, and then what angle is with the y-axis, and then that might make you turn somewhere else. Let's see, which way is it? Well, it doesn't matter. The point is, once you have three-dimensional angles all determined, then you are basically good to go. And yeah, all right. So then, how do you find the angles? You take the dot product with the unit vectors. That is, you take the dot product with ij and k, and to give you something. Let's see, yeah. And anyway, with that, we have, we're gonna skip the next example, 2.26, because the book wants to take vectors out of apples and oranges. I've never seen that before, so I'm gonna skip that for now. If I see the reason for that later, then maybe we'll come back to it. So let's move on. Okay, next we're gonna do projections. The projections is the one vector and the force or the component of one vector in the direction of another vector. That is, for example, there is say if you're pulling some cart like this, okay? Now you're pulling it on a rope, let's just say. So the force is following the rope, but the question is which part of that force is going forward, you see? And to do that, you are going to calculate the projection of the force vector in the other direction, the direction you want to know about. So which part, and to do that, we are going to do the dot product, I guess. And yes, you're going to find the cosine theta where I'm looking at the following page 156. Okay, the projection of V along something that makes an angle cosine theta is just the magnitude. That is, right now we're talking about the magnitude because we already know which direction is going. Right? The magnitude is this angle times cosine theta, and that comes from from theorem 2.4. Okay, you need to figure out what is that thing going in the direction with the angle theta. Then that's what you're gonna do. Let's see. So as a result, if you have a vector that you need to know how long it is in a certain projection of some other vector, then you have the projection then is equal to V times cosine theta, and that's coming from this equation. Or you can rewrite it as, after you're doing some substituting cosine theta for this equation over here, we have eventually you get the projection is also equal to u dot V divided by the magnitude of u. That is that's just the length though. That is that is the magnitude. Now if we also need to know its direction, then we can multiply this value here by the direction of u, that is the unit fact. What is it called? Doesn't matter. My point is you find the unit vector in the direction of u, which is you multiply it by, so you have this thing, okay, that's just the length of your projection, and you multiply it by the vector u divided by its magnitude, so that is the direct, so that gives you the direction because that's 1. That's a vector of a direction of 1, and that's its magnitude, and together you get the whole vector. Let's see, what's the last thing? The length is, well, the length is just that. I guess it's also called the scalar projection, well, whatever. The point is, that's what we're doing is if you need, see, just to find out the projection of v in the direction of u, we'll calculate the cosine theta to know how long it is, and then, but its direction is of course the same direction as u, and that is how this works. So with that, please do the homework of 2.27. Now so far everything we do basically is like, I don't know, trigonometry, maybe less. But that's important to do because we need to understand get a feel for the dot product. So even though the process is slightly tedious or very tedious, it still needs to be done. So please do the next example. Similarly, please do examples 2.28 and 2.29, where you're trying to find vectors whose projections are different at different angles or whatever. So then we come to the last concept on page 160, where we're talking about work. Okay, now work is, they define work like this. That is not the actual definition of work. Work is defined by as force times distance. That's the real definition in physics. But for now, we'll just go by what your book says. Okay, they want you to do work as force dot the direction of where the work is going. In this case, PQ. Is traveling from P to Q, and you have to do the dot product, which is the same as the magnitudes multiplied together times the cosine of the angle between them if the angle is not 0. And then that would be, yeah, I guess if the angle is 0, then it is, as I say, the work is given by force times distance that it traveled. So this equation then includes in case the force is going a somewhat different direction than where the object is moving. So anyway, having said that, please do example 2.30 as the last homework, and that concludes this section. Now for homework, please do, which is on page 162, please do problems 127, 33, 35, 39, 43, 47, 51, 55, 59, 63, 69, 71, 73, 75, and 79. Yeah, and I'm not going to talk about any of the homework because this is just, I don't know, basic trigonometry and basic algebra or something. So I'm going to skip the homework because I don't think you will have any trouble with it. In the next section, we're going to do the cross product, and that I will be doing the homework. All right? So